You have a terabyte-scale data processing job crawling along, and you need it faster. To speed it up, we have to look inside the physical hardware, the massive server racks and spinning cooling fans powering your cloud cluster. The standard intuition for making software run faster is straightforward. Add more processing cores to increase concurrency. You go into your Spark configuration and double the cores per executor from 5 to 10, while leaving the total memory fixed at 20 gigabytes. But instead of cutting the runtime in half, the entire cluster abruptly grinds to a halt and completely crashes. The system throws a terminal out-of-memory error, specifically Java heap space exhaustion. To understand why adding compute breaks the cluster, we have to stop looking at the code and examine the physical limits of the hardware itself. In a distributed system, compute and memory are physically coupled. Ignoring that relationship turns a simple processing upgrade into a systemic failure. Let's look at a multi-node cluster preparing to execute a basic SQL group by command. This command requires an operation called a shuffle, the mandatory redistribution of data across the cluster so that all identical keys end up on the exact same node. This triggers phase 1 of the operation, the shuffle write. If we have 10 executors holding 100 gigabytes each, exactly 1 terabyte of data is pushed directly into the executor's local solid-state drives. Phase 2 is the shuffle read. Tasks pull their required partition data from every single other executor in the entire cluster, simultaneously, over the wire. That exact same terabyte of data is now pulled entirely across the network. This creates a 2x penalty. 1 terabyte of input data demands exactly 1 terabyte of local disk writes, plus 1 terabyte of network reads. We have to contrast this massive physical data movement against strict hardware limits, specifically a standard 10 gigabit per second network connection. 10 gigabits per second equates to roughly 1.25 gigabytes per second of actual data transfer speed. At that speed, the CPU's processing power becomes completely irrelevant. The network pipes are completely saturated by the sheer volume of data in transit. A simple SQL command is a massive physical logistics operation that pushes standard data center hardware to its absolute throughput limits. If we zoom in from the wide network down into the internal architecture of a single executor node, we hit the next bottleneck, memory. An executor might have 20 gigabytes of total RAM, but that is not a single unified pool of available memory. As we see here, the architecture strictly splits the memory. Roughly 40% is reserved for storage and internal overhead, leaving only about 12 gigabytes as active execution memory for processing. Consider what happens when a massive 10 gigabyte data partition arrives. That partition must fit into the fraction of the 12 gigabyte execution memory allocated to that specific task, which is typically only about 4 gigabytes. This triggers memory pressure. Memory pressure occurs at the exact moment the data required by a task exceeds the physical RAM allocated to it. To avoid crashing immediately, Spark uses an automated survival mechanism called spilling, writing intermediate processing data down to the local disk to free up RAM. The hidden cost is severe. Spilling a single 10 gigabyte partition generates roughly 30 gigabytes of total disk reads and writes, because all those smaller spilled files must eventually be read back into memory and merged. While spilling prevents an immediate crash, it introduces a destructive I/O amplification loop, turning a minor shortage into a catastrophic disk bottleneck. This brings us back to our initial setup, upgrading the configuration from 5 cores to 10 cores inside a fixed 20 gigabyte executor. In case A, 5 processing cores run 5 parallel tasks. 12 gigabytes divided by 5 yields 2.4 gigabytes per task. Now look at case B. Upgrading to 10 cores forces 10 concurrent tasks into the exact same Java virtual machine. The effective memory available per task is instantly slashed in half, dropping to just 1.2 gigabytes. In a live system, these 10 tasks process heavy datasets simultaneously. This creates the danger of overlapping peak memory demands, particularly during a massive network shuffle operation. 10 tasks concurrently fetching data and building large hash tables in memory will instantly shatter the 12 gigabyte execution ceiling. There are secondary internal effects as well. Doubling the parallel tasks also doubles the required shuffle read and write buffers within that same tight space. This generates extreme garbage collection pressure. It's the automatic process to delete unused temporary objects to free memory, but an exponential increase in objects forces the system into complete overdrive. The final physical failure sequence begins here. 10 memory-starved tasks attempt to spill intermediate data to the local solid-state drive at the exact same millisecond. The local disk freezes under simultaneous write contention. Because memory cannot clear fast enough, the JVM simply gives up and throws a fatal out-of-memory error. Increasing concurrency within a fixed memory boundary does not scale compute. It scales resource contention, mathematically engineering a system crash. To scale distributed compute correctly, we have to respect the physical constraints of the hardware. The unbreakable rule of memory sizing is that task partition sizes must always remain strictly smaller than the per-core memory limit. We can also bypass heavy shuffles entirely by utilizing broadcast joins to copy small data tables directly to the executors. When you need more processing speed, the correct method is to leave the individual executor configuration at a highly balanced 3 to 5 cores. As shown here, the definitive solution for more processing power is to double the total number of executors in the cluster, instead of doubling the cores per executor. This scales your parallel compute capabilities while linearly expanding the total memory pool across the cluster. True distributed performance is achieved by respecting physical hardware limits and scaling the environment horizontally.